Hello juniors, we're going to continue now with electronic assignment 18, modeling periodic functions. We're going to see part 2 of this tutorial video. If you remember from the last video, we have seen the characteristics of a tangent function, and we have seen the first part for modeling periodic functions. We have seen an investigation, which is about the Ferris wheel, the London Eye, right? And we have analyzed how we can relate this situation, this real life situation, to periodic functions, right? We have found the function that describes this motion particularly. Okay. So now we're going to see some other examples. We're going to see this one and one last one over here in order to see how we can apply this to different situations. Okay. There's a video here which I'm going to be posting in the same electronic assignment as this one in the assignment in Google Classroom, where you will be able to see how or finish understanding in case you're not visualizing how circular motion works. If you see this video, it's a short one. It's just two and a half minutes approximately, where you're going to see how to visualize how a periodic or circular motion works. Okay, so let's see this example. It says Ben is a fisherman with a boat in real harbor. This is part of the graph of the depth of the water at the mouth of the harbor. Okay, so this is a situation in which the tide of the water level changes depending on the hour after midnight, right? That's something that normally occurs, right? We would say that during midnight the water tide tends to increase, and then during the day, during the morning, it decreases, and then again in the afternoon it increases, and then for the night it decreases again, right? So that's a real life situation that you can model, right, using this. And so it says, part A, find the amplitude of the function. In order to find the amplitude of the function, we already know how to do this, right? We can first of all identify the axis of this graph. Actually, the axis is not there. The axis should be at 5, right here. And or if you're not sure where the axis is, you can identify a maximum and a minimum point, for example. So in part A, let me do it here, we would say that the amplitude is half the distance from a maximum to a minimum, right? So we would write this as maximum minus the minimum value in order to find the distance, and we're going to divide this by 2 in order to have half of this distance. So the maximum value is 8, the minimum value is 2, so 8 minus 2 divided by 2, this gives us 6 divided by 2, that's 3, and that's the value of the amplitude, right? 3 meters would be in this particular case. That means that the value of A for our trigonometric function would be 3. Okay, but this is the answer. We're asked for the amplitude. Then for part B, it says find the period of the function. The period, as you know, is when the cycle repeats, right? An easy way to identify the period would be analyzing the distance between one maximum value and the other maximum values. The maximum values are also known as crests, right? Crests, or if you consider the minimum values, these are known as throws, right? Those are other names that were given to the maximum and minimum points. Okay, so if we want to find the period, for example, we could consider this maximum and this maximum and find the distance between these two, right? This would be the period in this case. Okay, so to find the period, we can subtract this value, 16, and this value here, and we will find the period, right? So it's 16 minus 4. So the period is 16 minus 4, and we're going to get as a result 12, and we're talking about hours, right? So it's 12 hours is my period. So every 12 hours, my cycle is repeating in this situation. Okay, so from the period, we could, for example, take the value of B, right? We know that the period is 2 pi over B, sorry. So the period is 12. So this is 2 pi over b. So by solving for b, we can have that b is equal to 2 pi over 12. And if we simplify this, we're going to get that b is equal to pi over 6. So we already have the value of b as well. Then, if we move on to part C, it says, find the horizontal shift. In order to find the horizontal shift, we would first have to identify whether we're going to work with a cosine or a sine function. I think it's easier if we consider this to be a cosine function, right? Because we have a maximum value here, and we know that a cosine function must start with its maximum value, so we know that there's a horizontal translation. Let me mark this maybe with a different color. We know that there's a horizontal translation here of 4 units. Let's see, 4 units, there you go, to the right. Okay, so this would be our value of C, 4 units to the right. Okay, so if we move on here, we know that if we consider a cosine function, we can see that the function is translated 4 units to the right. That means that the value of C would be positive 4, right? Positive 4 is the value of C. So that is the horizontal shift, 4 units to the right. So we can mark this as our answer for part C. And finally, we're asked for the vertical shift. In order to find the vertical shift, we need to identify where our axis is, right? We could visually state that it is 5, but if you want to find the exact value in case you're not sure, it's basically finding the midpoint between the maximum and the minimum value. In order to find the midpoint between the maximum and a minimum value, we would have to add both values and then divide by 2, right? In order to get the average or midpoint, okay? So we're going to write this as vertical shift is equal to the maximum value plus the minimum value divided by 2. So you see it's kind of the same calculation as amplitude, but instead of subtracting, we're adding the values. So this would be equal to 8 plus 2 divided by 2. 8 plus 2 is 10, and divided by 2, that's 5 meters, okay? So that's our vertical shift, which means that our value of D would be equal to 5. And with this, we confirm that the axis is at 5, right? So here's the axis, and this value is 5 over here. Okay, so now we have all of the elements for the trigonometric or periodic function, right? We have the value of A, we have the value of B, we have the value of C, and we have the value of D. So with all of this information, for part E, it says write down the equation of the function for the depth of the water in terms of M and H. Okay, so we're going to write our equation, which would be M is the depth in meters, and H is the hours after midnight. So our equation would be M is like our Y, right, is equal to A, remember the general, let me write the general first. The general equation, the general function is always equal to A times cosine of B times X minus C plus D, right, plus D. So our equation in this case would be M, which is Y. M is equal to, the value of A is 3 times cosine of B, in our case, is pi over 6. So pi over 6 times X minus 4, which is our value of C, plus 5. Sorry, instead of X, we need to write H, because our X value is H in this particular problem. So this would be the equation or the function in terms of M and H. Okay, this is the answer for part E. Let me check this. There you go. Okay, finally, or then for part F, it says calculate the depth of the water at 9:30 a.m. Okay, so for part F, remember we cannot plug in 9:30 as it is here. We need to turn 9:30 into hours, right? So we could say that 9:30 a.m. is the same as saying 9.5 hours, right? So we can plug in this value of hours into h here, and we're going to get the depth in meters. So you see how we can use this model already in order to find the depth of the water. So we're going to say that m is equal to 3 times cosine of pi over 6 times h, which is 9.5, minus 4 plus 5. There you go. So if you use the calculator for this, let me show you. So if you use the calculator, remember the first thing we need to check is that our calculator should be configured in radians. It is, so we're fine. So now we're going to plug in the information. 3 times cosine of pi over 6. Sorry, I'm going to use parentheses. Pi over 6 times 9.5 minus 4, and then plus 5. So there we have the depth of the water for this case, right? So m is equal to 2.10 if you leave it in 3 significant figures. And we're talking about meters, I think, right? Let me check. The depth of the water, yes, this is in meters. Okay, so at 9:30 a.m., the depth of the water would be 2.10 meters. Finally, for part G, it says find the next. It says Ben's boat can only get in and out of the harbor when there is at least 4 meters of water at the mouth of the harbor. Ben sleeps until 10 a.m. Find the next time that he can go fishing. Okay, so here we have an interesting analysis. We need to see when the function is above 4 meters. So if you take a look at here, we can trace this line here for 4 meters. And we know that, well, first of all, Ben sleeps until 10 a.m., right? So when he wakes up, he still cannot go out of to the harbor, right? Because we are in a depth below 4 meters. So he's gonna be able to go out at this time right here, which would be maybe 12 point something. And then again, he would be able to go out at this time, right? Over here, which would be around 19 point something, right? Hours. But we're interested in this first time, right? Because the question says find the next time that he can go fishing. So basically, to find this point of intersection over here, we need to set the equation to 4, right? So we're going to write this down here first. We're going to say that the depth of the water should be 4. This is equal to 3 times cosine of pi over 6 times h, we don't know that exact time, minus 4 plus 5. So how can we solve this? If we're able to use our calculator, then we're going to use it in order to find this exact value, because trying to solve for h here would get kind of tough, right? You can, but you're going to waste too much time. If you're allowed to use calculator, then that's much easier. So how do you do that? If you go to menu, graph, first of all, we would have to plug in the equation. So we would write, the first equation is the trigonometric function, right? We're going to write 3 times cosine of parentheses pi over 6 times x, remember you should write x minus 4 plus 5. And then we have another equation, which is, we want to set this to 4, right? So our second function would be y equals 4 only, okay? And we draw this. Probably we won't have the graph clear there, so we will need to change our scale, shift V win. In this particular case, our minimum value of x would be 0. It's the minimum value here. The maximum would be 24. And our scale is of 2, right? Then the minimum value of y is again 0. The maximum value is 8, as we can see in the graph. And the scale is 2 again. So then we can draw this and we're going to a much clearer view of the situation, right? So we have the depth of the water, which is a blue curve, and then y equals 4, which is a straight red line over there. So if we click on Shift Intersect, Shift G Solve Intersect, we get this first point, but Ben is still not awake for this time. Then for this time over here, 7.6, Ben is still not awake. And this would be the correct answer, right? Which is the intersection we're looking for, right? So if we, let me write the steps here. So using GDC, graph both functions, and then find intersection points. Let me write that down here. Find intersection points. So we get that the first time where he can get out is at h equals 12.4 if we round these to three significant figures. That means that around this is kind of like 12:20 a.m., right? Around 12:20 a.m. he will be able to get out again, or get out of the harbor, basically, right? If you want, you can convert this to hours in this format, but if you leave it like that, it will be fine, unless you're specifically asked to find it in that way. Okay, so the next time he can go fishing would be at least at 12.4 hours, right? He could go a little bit later than that, but the first time where he can get out is at 12.4 hours. Okay, so I hope this is getting clear for you people. Now let's see this last example where it says the function, and we're given the function, right? It's a cosine function, and we have all of the values, A, B, C, and D already. So this should be easy, right? Can be modeled to use the height of a passenger above the boarding platform on the London Eye. Use this function to estimate the height of the passenger above the platform at 8 minutes after boarding, 19 minutes after boarding. Okay, so this part is easy, right? If we want to find the height after 8 minutes, this is a function of height with respect to time, right? So we would just have to replace this value of time into our functions, right? So the first height at 8 would be equal to 67.5 times cosine of 2 pi over 30 times 8 minus 15 plus 67.5. So if you solve this using the calculator, you should get the answer. Let's see how much that is. We go to menu 1, erase this. So we would have 67.5 times cosine of 2 pi over 30. This is being multiplied by 8 minus 15, and then plus 67.5. Click on execute. Remember, calculator should always be in radians, and we get this value of 74.6, and this is in meters, I think, right? Height of the passenger is meters. So this is our first answer. Then for the second part of A, it's the same question, but now for 19 minutes. So we're going to do the same thing, h of 19 in this case. So we copy exactly the same thing, 67.5 times cosine of 2 pi over 30 times 19 minus 15 plus 67.5. So if we plug in that information in the calculator, we would just change the value of this 8 over here, and we're going to get, as a result, 112.7 meters, or 113 meters if we round this to three significant figures. Okay, so that'll be the answer for the second part of A. Finally, for part B, it says use this this function to estimate how long it takes for the passenger to first reach a height of 100 meters. Okay, so this kind of follows the same concept of what we just saw before. we want to find the first time it reaches 100 meters. So we can set the whole equation or the whole function to 100, right? 100 meters is equal, and we copy the function 67.5 cosine of 2 pi over 30. Instead of writing height time, we're going to leave it as t. We want to find the time it first reaches that value, plus 67.5. But once again, if you're allowed to use calculator, it's much easier if you graph all of this and then find the first intersection point in order to find the first time it reaches 100, right? So basically, we're going to follow these same steps we did here. So let me copy this. So using GDC, we're going to graph both functions. The first function would be obviously the periodic function, and the second function is y equals 100. And we're going to analyze the intersection point. So let me do that here. Menu graph. I'm going to erase this 2. So the first function will be 67.5 times cosine of 2 pi over 30. 2 pi over 30 times x minus 15, parentheses, plus 67.5. And the second function would obviously be 100, right? We want to find the intersection point between these two. So we draw. We will probably not be able to see this, so we need to change the scale. To change the scale, we would have to analyze our minimum value of x would be 0, that's fine. Sorry. Shift V win, that's fine. The maximum value we're talking about London 9, right? Maybe we can try, if we're talking about 8 minutes and 19 minutes, we can exaggerate and put 60, for example, on a scale of 10, that's fine. Then the minimum value could be 0, or we're talking about height. Our maximum value should be double this value, would be 67.5. We can try 150 to exaggerate a little bit. Scale, we could write 10, that's fine. And we should be able to see the graph now. Let's see. Yes, there we have the function. So we have the model of the situation. And you see that the red line here is the height equals 100, right? So this first intersection right here is what we're interested for in this problem, right? So we're going to go to Shift G solve intersect, and that's the first intersection. You see that the value of y is 100, and the value of x, or the time where that occurs, is at 9.90. We're talking about minutes here, right? So if you do the sketch, you're gonna get that the time of first intersection would be 9.90 minutes. So that's the first time in which we're gonna get 100 meters in height, right? If I show you what I did here, it's basically this, right? This is using Desmos. You see that I graph both functions, and the first intersection point occurred at this point, okay, which is 9.90 minutes. And that's it. So you see that this is not difficult, right? If you really understand what a periodic function is about and how to properly use a calculator, then you shouldn't struggle much with these types of problems. So I hope this was clear, juniors. You're going to be practicing later on with exercises. If it's not clear, please let me know, and we're going to clear it out in future live sessions. Thank you for your attention, and see you.